Lecture 9. So in the last time, we started working on the design of static design for the static loads. And we looked at modes of failure, which is like rigidity based, strength based, and other fracture based. And then we talked about uncertainties leading into the factor of safety. And after that, we also looked into some fundamental equations. Those fundamental equations are first one, for the tension, we said sigma is equals to P by A, right? Where P is the normal force, A is the normal area. Second, shear stress tau divided by the normal area that has to be into the picture. Then we also looked for the bending stress. For the bending stress, we have seen that sigma is equals to my by I using Euler-Bernoulli beam theory. Then we also looked at shear stress due to the torsion. As tau is equals to T rho by J, where I is moment of inertia and J is polar moment of inertia. And then rho is the radius, T is the torsion, or simply call it as torque. M is the bending moment, and Y is the height from the neutral axis. So these things we have used all these fundamental equations, and using these fundamental equations, most of the designs are simplified because any uncertainties are taken care by making use of the factor of safety. Further, this is only, these fundamental equations are mostly valid for one-dimensional stress state, whereas you know that stress at any given point is triaxial in, right? Stress in the biaxial state of stress can be defined as, if you have a single piece of a quad, this is sigma xx, this is sigma x with the y direction, this is sigma yx, this is sigma yy, and back and forth. All other components can be written. So sigma for a two-dimensional state is written as sigma xx, sigma xy. Since x and yx is symmetric for material, then we can write sigma xy, sigma yy. Sigma xy is equals to sigma yx for when body movements are absent. So because of this symmetry, we have these kind of states. Further, if I look at triaxial state of stress, right? The triaxial state of stress would be something like this. Sigma xx, sigma xy, sigma xz, sigma yy, sigma yx, sigma yz, and so on and so forth. You can like this is sigma zz, this is sigma zx, this on this face, this one is sigma zy. So the triaxial state of stress, again by sigma xy is equals to sigma yx, sigma y, and sigma zx is equals to sigma xz. These body moments are absent. So in this, then our stress would look symmetric. Sigma xx, sigma xy, sigma xz, sigma yy, sigma yz, and sigma zz, and this is the symmetric part of it. So this value is same as this value, this value is same as this value, this value will be same as this value. Now this is the triaxial state or 3D thing. Similarly, one can also write triaxial state of strain as epsilon xx, epsilon xy, epsilon xz, epsilon yy, epsilon yz, epsilon zz, be epsilon x y is equals to 1/2 dou u by dou y plus dou v by dou x, and epsilon the same as epsilon yx, epsilon yz is equals to 1/2 dou v by dou z plus dou W by dou Y. Dou U by dou Z plus dou W dou X is equals to epsilon Zx. Similarly, epsilon Xx is equals to dou by dou X, epsilon Yy is equals to dou V dz is equals to dou W by dou Z. Now, if you look at it in a one-dimensional state, the stresses were much simpler. It's only one component is there. Whereas in the two-dimensional state, you have three independent stresses. This is 1, this is 2, and this is 3. Whereas in the three-dimensional state, you have 1, 2, 3, 4, 5, 6. So depending upon how you want to analyze your continuum, if you want to analyze in three-dimensional state, you have to deal with higher number of stresses. But it's an only most of the time an approximation that you make it and solve it in 1D, but not all problems can be solved in 1D. So one needs to understand that in certain problems one has to do with one-dimensional state of stress, one-dimensional analysis, two-dimensional analysis, and three-dimensional analysis. So one such kind of dimensional reduction is plane stress and plane strain condition. In plane strain condition, which is P epsilon, your epsilon ZZ is equals to 0, epsilon XZ is equals to 0, epsilon YZ is 0. Further, your U is only a function of X and Y, it is not function of Z. Similarly, your X and Y is a function of thing. So because of these things, what you will end up is a dimensional reduction in the plane strain condition, in which all other stress traits are available except these things will be there. Similarly, the easiest case of such thing is like let's say this dam is running all throughout. If you take any given cross section like this typical cross section is constrained by any other cross section from either direction, and it has a lateral restraint in the z direction. Let's say this is your z direction, which there is no movement in the third direction, because and hence any given further this cross section has to be in plane loading, that is U is a function of X and Y, and that automatically says that one. And because of which you can still have epsilon ZZ not equals to 0, epsilon further epsilon XZ is equals to 0, sigma YZ is equals to 0. Similarly, if I take plane stress condition, the plane stress condition is in this, your sigma ZZ is equals to 0, epsilon sigma xz is equals to 0, sigma yz is equals to 0. Your u is a function of x comma y, and v is a function of x comma y, and w is not existent. But in this case, we are analyzing very thin cross section. In the thin cross section, there is, let's say this is the z direction. There is no variation of the things in the z direction because thickness is very small. Further, the loading is within the plane. That's the reason it is xy. In these cases, because of the Poisson's effect, you will have epsilon zz not equals to 0, but epsilon xz is equals to 0, epsilon yz is equals to 0. So when you have very third dimension is insignificant with respect to the x and y dimension, then you make plane stress reduction. When you have similar this kind of the third side constraint is you have so much infinite constraint, then the cross section of it, if you can't do that, then you need to go and solve a full 3D state. When you solve a 3D state, you link a triaxial state, that which you are presenting in this. Now, in order to handle a one-dimensional, two-dimensional, three-dimensional state, we need to understand several different things. So for that, what I will do is I will try to convince you that the better way to represent these things is not the full form what you are seeing, but there is something called as principal stresses. Okay, so let me convince you through a 2D example. If I take a 2D stress state and I want to motivate you to think about the principal stresses. So what are these principal stresses? Now let us consider a small piece, a small box, something like that. Let's say if it is subjected to shear, it will have a shape of Kaju Katli, right? So it will have a shape of something like that if it is subjected to shear. So if you subject this box to pure shear, it will end up in this deformed configuration, which is like in the shape of Kaju Katli. Now, what I want to convince you is, if it is subjected to pure shear, then if you are looking, I will again redraw the side. So you see that one direction, this principal direction, is being stretched, whereas this direction is being compressed. So if I take a small element which is in the 45 degrees in this manner, right? Because this is being elongated, so this, let's say I call it as A side and B side. This is the A side and this is B side. A is being stretched and B is being compressed. So this is what is the stress state at a degree 45 degrees to the horizontal for a pure shear condition. That means any given stress state, when you transform with respect to your coordinates which are rotated by angle theta, then it will have different components. That is, if I have a stress state, a generic stress state, this is generic, not pure shear, generic 2D stress state, which is sigma xx, sigma xy, sigma xy, sigma yy. If I'm looking through this as x and y system, I'll have the sigma as sigma xx, sigma xy, symmetric, sigma yy. Now, if I start looking with an axis, which I call it as x dash and y dash. Now, instead of looking from x and y, I start looking at x dash and y dash. Then I will have the things which should look like sigma xx dash, sigma xy dash, sigma yy dash, which is again symmetric. These components are not same. The one who is looking in the XY system will have some set of sigma tensor, and if he's looking from x dash and y dash, he will look at different component values, but both the things is representing the same system. It is the same system, but this guy is looking into this guy is automatically can be considered as taking a small box which is inclined at a theta direction, and we are looking at what is sigma yy dash, sigma xx dash, and so on and so forth. So this is what we are looking. Depending upon the orientation of the box or the control volume, whatever we are looking at, or as element, the rotation of the element will dictate how this looks like. Then how this is what is called the X from this state to this state is called stress transformation. Now, how this stress transformation has to relate with the principal stresses has a role to play. That one is when you rotate in this manner, there is one angle which is called, if theta, this theta is equals to theta p, then your sigma, the same sigma, would look like sigma 1, 0, 0, sigma 2. Now, the good part about this guy is, let's see what is the good thing about this. Off diagonal terms are 0. That implies no shear stress. That implies purely dilatational. Purely dilatational in nature. So, what we are saying is, in some orientation, the fibers are stretched through the dilatation, and those dilatational values are called sigma 1 and sigma 2 are principal stresses. Okay, these things you might have learned in your previous course in strength of materials, where you call it as for a plane stress condition, the stress transformation equations are given by this. I will rewrite it instead of deriving it. For plane stress condition, stress transformation is sigma xx dash is equals to sigma xx plus sigma yy sigma xx dash is equals to sigma xx plus sigma yy by 2 plus sigma xx minus sigma yy cos 2 theta plus tau xy or sigma xy, both are same, sine 2 theta. Sometimes I call sigma, interchange the notation, so don't get confused. And similarly, your tau xy or sigma xy dash is given by minus of sigma xx minus sigma yy by 2 sine 2 theta plus tau xy cos 2 theta. Now we are looking for, now if I want to find theta p, how do I get it? Theta p is a state in which sigma xy dash is equals to 0. So if I equate this equation to sigma equals to 0, then this equation will be this equation. I can write it as sine 2 theta p by cos 2 theta p is equals to tau xy by sigma xx minus sigma y by 2. I will put it here, so which is nothing but tan 2 theta p, or your theta p is equals to 1/2 of tan inverse 2 tau xy similar sigma xx minus sigma yy. Similarly, there can be an angle at which this is sigma theta p is principal planes. So if you substitute this theta p in this value, whatever you get is your principal stress values. Okay, so the one sigma yy dash would be, so if you want to write sigma yy dash, this would be same, only thing is this is same, this is minus sign, all the other things are same. So this is same, this is same. This would be also again with a negative sign. So or let me rewrite it for the sake of kind of clarity. So sigma yy dash is equals to so now these are your the principal stresses are obtained when you take this theta p, substitute here, you will get sigma 2, and when you substitute, you will get sigma 1 and 2. Sigma 1 is the highest value, sigma 2 is the lowest value. Now similarly, there are planes where your shear stress is maximum. And those planes are obtained when theta is equals to theta s, that is equals to minus of sigma xx minus sigma yy divided by 2 tau xy. Now, these kind of equations can be easily obtained by what is known as concept of Mohr's circle from your strength of materials. Okay. Okay, let's get back. So now we will understand how to see. Remembering this set of equations is always difficult, but all this stress transformation can be done in much easier manner. You know something called as a Mohr cell concept. So let us write what is a Mohr cell. So for that, let's take a two-dimensional plane stress or sigma xy, whatever you want to call. Now let's draw an x-axis and y-axis. Let's call this as normal stresses and let's call this as the shear stresses. Okay, now we have drawn this one. Now take these two values. Now when you are taking these two values and plot it as one point there. Now when you are plotting it, this normal stress, let's say sigma xx is coming here, and now you need to plot tau xy. You want to plot it on the upper side or lower side. So for that, what we'll do is, when you have your shear stress, any shear stress that gives you a clockwise thing can be considered as negative. The shear stress which gives, so this is anti-clockwise. So you take a moment about this point. So this would, about this point, this would be rotating the box in the anti-clockwise. If you take this one with respect to this, which is tau yx, this is tau xy, this would be rotating in the clockwise manner. This is clockwise. The same shear stress would give you positive. So this is my notation. I mean, if you want to reverse it, you can reverse it, but be consistent all throughout. But in this course, we will try to use this as our notation. So any shear stress that gives you an anti-clockwise will consider as a negative shear stress, and any shear stress that gives you positive things, that will be positive. Now you take this one. Let's assume that this is giving a negative shear stress in this axis, and this is your sigma xx. So this point is sigma xx comma tau xy. Now similarly plot this point. In this point, this is tau yx, which is same as that, but even though the values may be same, this guy is giving a clockwise moment. So it has to be on the positive shear stress. Now let us say your sigma yy is some, these are just symbolic. I choose this to be sigma yy, and my shear stress of same magnitude as this one has to be y comma tau yx. Now with this as one end and this as another end, join these lines. So we have joined these lines. Now using this, draw a circle. I'm very bad at drawing these things, but let's assume I'm drawing a circle. So yeah, it's a very bad circle. Yeah, I'm bad at drawing, as I said, but let's draw. If you can draw it simply, this using this as the radius, this is called as Mohr's circle. Okay, so this now when you so let's this as a diameter, you have drawn the things. Now it would intersect the normal axis at this place and at this place. The highest value you will call it as sigma 1 and the least value you call it as sigma 2. At this place, what is the y-axis? The y-axis is 0. That is, the shear stress on this element is 0. So if you look back, your sigma 1 and sigma 2 are these things. Sigma 1, 0, 0 and sigma 2. Now, what is the theta p or 2 theta p? This angle, this is as the center of the circle, Mohr circle. This angle from the original plane to this value is your 2 theta p. And from here, if I take, this is my radius. At this place, this would be maximum shear stress. So from here to here is my 2 theta s. All the things that we have developed here, this theta s and theta thing, can be easily obtained from this manner. Okay, if you use this as the angle and calculate your based on your trigonometry, you'll find that all these values can be obtained from that. Or, and in contrary, you look at this thing, this represents the equation of a circle. So these three would represents the equation of the circle, and hence one can clearly say that there is either you can do stress transformation using this set of equations, or you can simply draw a Mohr circle and get the things done. Now, if somebody asks you to find out what is the stress state at an angle theta, if somebody asks you to get an angle theta, then starting from this as the base thing, try to rotate it by 2 theta. And at that place, touch the radius to the Mohr circle. And that would be your tau xy dash, and this is your sigma xx dash. Similarly, if you extend it on the other side, you will get your tau xy dash and sigma yy dash. So that is how a Mohr circle will represent all the possible states of the stress transformation. Okay, so now this is very useful. Now, why this is useful, we'll come to know when we are doing the theories of failure. Okay, so this concept we are done. So what we'll do is we'll consider, I would suggest you should practice how to draw Mohr circle for different stress states so that you get much more acquaintance. But now I will do it an example of pure shear, okay, which I have said earlier, so that I will convince you that what we have discussed earlier is not a bad thing at all. So pure shear is a pure shear in which, if you consider a box, you're applying a shear stress on all the four sides equal to tau xy. This is tau yx. Both are same. So if I draw Mohr circle for this kind of a stress state, sigma, and this is tau, On this there is no normal stress, so this is 0, and shear stress is in the clockwise. So this stress state is a similarly the point on this is obtained as this fellow. Now this as a diameter, I need to draw a Mohr circle. So this as a diameter, if I draw a Mohr circle, now this is your radius, this is your radius, this is your radius, this is your radius. So if this is radius and radius is equals to tau xy or yx, then this normal stress at this place is also tau xy, and your shear stress is 0. This is tau xy comma 0. The first one is normal stress, second thing is x coordinate is normal stress, y coordinate is shear stress. So what is your sigma 1 and sigma 2? Sigma 1 is given by tau xy and sigma 2 is given by minus tau xy. So as I said earlier, in the rotated 45 degrees, because now you see what is the angle between this to this state, it is 90. If it is 90, half of that should be 2 theta p. If 2 theta p is equals to 90 degrees, theta p is 45 degrees. So at 45 degrees, this element is subjected to plus tau xy 0, 0 minus. So that means the stress state for the blue element is like it is pulling in the A direction, which we called earlier A, and it is compressing on the B direction by tau xy magnitude. So either you can draw the Mohr circle like this, or you can do all this stress transformation, find theta p, and get the same things done, right? So this is what is called stress state. If you have any questions on the Mohr circle, please let me know, because this is one of the important concept that will be very helpful in your a lot of analysis. If there are no questions, we'll continue with our theories of failure. Now, once we know how to handle a multi-axial stress state, similarly, you can have Mohr circle can be only drawn for the two-dimensional stress state. For the three-dimensional, there is nothing like a Mohr circle or a thing. But for any given a plane, if you cut a plane section on the redraw the Mohr circle. So with this, the next topic we will do is theories of failure, and in the theory of failure, we'll make use of all the stress transformation and that we have derived just now. So the first one in the theories of failure, it can also be summarized as excessive elastic deformation. The next one is failure due to generic or general yielding. So this is because of plastic deformation The third type of failure is fracture. In this, the specimen breaks into two or more parts. Now, in order to study these kind of failures, there are several theories that has been proposed in the past, and in this course we will only cover only some important failure theories that are relevant for the mechanical engineers. Okay, so shear stress theory. This has been done by several people like Coulomb, theory. It's been proposed by Huber von Mises, Henke's theory. These theory is quite important for the ductile materials. Then the later versions has also been obtained, like ductile, Coulomb, Mohr theory, then maximum principal stress theory, also known as Rankine's theory. Then for the brittle materials, we have brittle Coulomb Mohr's, and we modified Mohr theory. Maximum strain theory, or also known as Saint Venant's theory, and we have maximum energy theory, also known as Higgs theory. Now, out of all these things, you need to understand that several theories are proposed for a reason. There is no universal theory. Each type of material, same material at different temperature would behave in different manner. For example, even if you take metals which are very ductile in nature, and if you are subjected to very low temperatures, at this very low temperatures, they behave as like a brittle material. The same ductile theory which you are using it at at a room temperatures cannot be used at low temperatures. Similarly, the same metal, when it is subjected to very high temperatures, such as the combustion chambers in aero engines or something like that, there the metal flows under the influence of the distortional theory would fail. So you need to understand that there is no one single universal theory to predict the failure. There is a small window of applicability for each and every theory. That's the reason several theories have evolved in the literature, and we need to know the limitations of the theory and its applicability for a given set of material for the given loading conditions. Okay, so with this, what we'll do is, for some of the theories, we'll go in detail and list out the theories of failures, and with this theories of failures which we'll be using in the later part in the designing. All right, first one is shear stress theory, which would be Coulomb or Tresca guest theory. In this theory, yielding begins whenever the maximum shear stress in any element equals or exceeds the maximum shear stress in a tensile test specimen of the same material when that specimen begins to yield. One more thing I would like to say is when you are performing an experiment, for example, in your strength of material labs, you might have already done this uniaxial, tensile, or a compressive testing. And in this things, you might have just plotted a stress strain curve, right? You might have plotted a stress strain curve, and but you need to understand that from the previous things that the material drags. If you want to perform an experiment using a triaxial state, then how many experiments are required to obtain this kind of characterization curve such as this in a one-dimensional state? The answer for that is you need infinite number of experiments to be performed. So you cannot have an infinite experiments to be done to characterize one single material to totally define it, which is beyond our capability. Then how we can make sure that our design or our the strength is captured when it is in the multi-axial state. To do that, some of these theories will help you to understand it. Especially, we'll come to know in the next part, which is Huber-von Mises theory, that an equivalence between a multi-axial state as well as a uniaxial state was brought about, and that equivalent strain stress is popularly known as von Mises. So either you load them in a multi-axial state, but he will give you one equivalent uniaxial. So that will come to in the next chapter, next section. But you need to understand that all these theories are very close. So even in this theory, you have two-dimensional or three-dimensional shear stress are there. And what do you want to say for different combination of loads? So for that, what they proposed is consider test specimen under uniaxial load, that is sigma xx is equals to sigma xy equals y. Things are zero, will occur when sigma is at sigma yd. We'll also assume that this is uniaxial tension. Even let's assume that uniaxial compression is same. For that assumption, let's assume S by T is same as the same strength is there even when you are performing a compressive test, uniaxial compression. This is we would assume it. And based on this assumption, maximum shear stress tau max in this case is given by sigma 1 by 2, that is equals to SYT. Based on the Tresca criteria, is also this criteria is popularly known as Tresca criteria. Under biaxial loading in a plane, if mod of sigma 1 is less than ST, second mod of sigma 2 is less than YT, and x less than SYT by 2, then the yielding occurs. So using this, one can say that tau max is nothing but, using the Mohr circle, it is the sigma 1 minus sigma 2 is the diameter, by 2 is the radius. So we can say that sigma 1 minus sigma 2 criteria, this is the same, to be less than SYT. So using all this 1, 2, 3, the safe region is nothing but elastic region, can be plotted. First, let's this is sigma 1 and sigma 2 plane. This is sigma 1, this is sigma 2. If it is in the positive side, this would be your sigma 1. Side, the first two criteria says these two in the positive side and the negative side. Positive and another is negative. In such kind of a scenario, your shear force, your shear stress is ruling it. In those cases, you will have this as the criteria. This is the equation of a straight line with a negative slope. This is also equation of a straight line inclined at 40. So you can see that this equation of a straight line is manifested here. This is maximum SYT. This is SYT. SYC and SYT are same. So I will write it. And this is the thing. So this or failure locus is your yield or a fail locus. Inside this region, because it is elastic or not a failure, and if it is on this yield locus, then it represents the failure. This is the first criteria, second criteria. Let me put it this as first, second, this is first, second, the third criteria. In the different rates, this will completely define, this is shear stress criteria. Now there is second kind of criteria, which is Coulomb-Mohr theory. Coulomb-Mohr theory in the ductile Coulomb-Mohr theory, your SYC is not equals to SYT. In that cases, what will happen? E locus and sigma 2, let's say this is yes, which is same in the tension side, whereas the more this side is same as this side. So E locus, which would this one would be distortion. In the distortional energy theory, in order to develop this, I would just take a detour. Before that, let's write it up something. So in this, okay, if you have a spring, right, force is given by K, which is stored is nothing but a force multiplied by the displacement. Force into displacement, and since it is quasi-static manner, it is this 1/2 square. Similarly, for as, let's say, if by V, in the same manner, 1/2 K by it's okay. What we'll do is the equivalence, not derive it. So for uniaxial things, U is the strain energy per unit volume. Show that the same thing you need to understand is K unit length. So in the similar nature, if you want area, then this half epsilon square. Similarly, for a three-dimensional state, U, this is strain energy per unit volume is given as sigma xx square plus epsilon xy whole sigma x. You add up all the components, or you can write in terms of principle as sigma 1 epsilon. There is some small mistake. This is not into half, because when you write in terms of stiffness, then you will get the square. So I can write this in terms of square as something like this. This is also equal to, if I write sigma is equals to E epsilon, then I can write it as half E epsilon manner. So in terms of principle, where you sigma 1 minus of sigma 2 plus sigma 3, and similarly write epsilon 2 by rotation sigma minus mu sigma 3 epsilon 3 E sigma 3 mu C3 plus, plus by rotation, and is given by n plus sigma 2. Then whereas if you want to compute your U as on dilatational, U d. So dilatational is volume changes. This is due to shape changes. So we know that plasticity is because of the shape changes, as we discussed several times. So one, we can write this U dilatational, which we call it as UV plus UD. So UV can be obtained as by 3 sigma average whole square by 2E 1 minus 2. Now you know UD is nothing but U minus UD. If you compute, you will get it as 1 plus mu by 6E sigma 1 minus sigma 2 whole square in terms of principal stresses, sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square will be given as the thing. Now, at this point, what von Mises has said is there is an equivalence. There is an equivalence between a uniaxial stress state and a multi-axial stress state, provided they both have same distortional energy. The distortional energy is nothing but deviatoric energy. So it's like, for example, in your class, there may be several students who has the same CGPA or same marks. So in individual subjects, they may have scored differently, but when you sit for a placement, if somebody, two persons comes with 90% marks, they will both be considered equally same. In some subjects, he may score more, some subjects may be less. Same thing with the other guy. But as a cumulative, if both are exactly on dot as 90%, then they will be given appropriately same placement or whatever it is. So like that, what we are saying is there can be two different stress states. Each components can be different. Sigma xx can be different, sigma yy can be different, xy can be different, yz can be different. But if these two states, whatever may be the states, if their distortional energy are same, then they are equivalent. That's what they will have same yield locus, or they will have yielding at the same place. That is what has been done. So since we have done for a uniaxial stress state, a uniaxial stress state, when we are doing stress strain curve, in a uniaxial state is sigma 1 0 0 0 0 0 0 0 0. If you do that, your UD, this is UV. One plus mu by 3 sigma 1 square. SYT. So we know this as the yield criteria. Now take this one and equate it for this one. because this is for the multi-axial stress state and this is for the uniaxial state. And assuming that they both have same distortional energy, that will give you your distortional energy theory. That is, on equating, you'll get sigma 1 1 minus sigma 2 2 whole square plus sigma 2 sigma 3 whole square plus sigma 3 minus sigma 1 whole square has to be less than 2 times SYT whole square. This is for such kind of things. For example, for biaxial stresses, that is when sigma 3 is equals to 0, this is for the triaxial, then it will become even more easier. It is sigma 1 minus, sigma 1 square minus sigma 1 sigma 2 plus sigma 2 whole square under root square root has to be less than SYT is the yield locus. When we try to plot this distortional energy theory, first let's draw the Tresca criteria. This is Tresca. Distortional energy are also known as von Mises. This is this theory. It is something like this. It would go, it's an ellipsoidal equation. It's an ellipsoid. So this is, so based on that, you can, for example, if you want to write it in case of a pure shear, where sigma 1 is equals to minus sigma 2 is equals to tau xy, we can show that SYT is equal to square root times of tau xy. That makes that the yield, the strength in the yield is given by SYT divided by square root of 3. That makes it as 0.577 SYT. You see that people generally consider, in most places, people approximate as approximation 0.5 times SYT is generally used. Whereas if you predict from the distortional energy, you can see that it is given by 0.5. And tomorrow we will, Friday we will again resume with the rest of the failure theories. Till then, have a good time, and we'll meet you again back on Friday with rest of the theories of failure.